In this module, we shall first see a generalization of Lagrange's mean value theorem, commonly known as the ratio mean value theorem or the Cauchy mean value theorem or the generalized mean value theorem. And then we shall apply it to prove the famous L'Hopital's rule that is applied right and left by JEE students without actually knowing what the statement is. So let's begin with the statement and proof of the ratio mean value theorem. Ratio or Cauchy or generalized mean value theorem. So the statement is as follows. Instead of one function, we now have two functions. If f and g are continuous on the closed interval AB, differentiable on the open interval AB, then there exists a point C in the open interval AB such that f of b minus f of a, so far this looks very familiar, but into g prime of c is equal to, as you can guess, g of b minus g of a into f prime of c. Now it might be perplexing why this is called the ratio mean value theorem. Well, if g prime is never 0 on open interval AB, then of course I can write it as ratios. F prime of c by g prime of c is just equal to f of b minus f of a by g of b minus g of a. Fine. Now this is the generalized mean value theorem, simply because if you take the function g to be the function g of x equal to x, the identity function, you recover the Lagrange's mean value theorem. Another comment to be made, the eagle-eyed reader might be wondering why this is not 0. Well, it is not 0 because we have assumed g prime is never 0 on AB. Think about why g prime never being 0 will force g of b not to be equal to g of a. Okay, so let's prove this. The proof is not really hard. Proof. Well, as you can guess, we are going to apply Lagrange's mean value theorem to a special function. Well, we just choose h of x to be equal to f of b minus f of a into g of x minus g of a plus minus g of b minus g of a into f of x minus f of a. Okay, so we are just going to apply Lagrange's mean value theorem to this function. First, let's check what h of b is and what h of a is. Well, by the way things have been chosen, when I substitute x equal to b, everything gets cancelled and you get 0. And when you substitute x equal to a also, you get 0. That's the way these functions have been chosen. So you don't even need to apply the full force of Lagrange's mean value theorem. Just by Rolle's theorem, there exists some c in AB such that h prime of c is 0. Right? Now you can immediately see that h prime of c is nothing but f of b minus f of a times g prime of c minus g of b minus g of a times f prime of c, and this is equal to 0, and this concludes the proof. The second part, where I'm assuming that g prime is not 0 everywhere, follows immediately. Okay, so now we are going to apply this ratio mean value theorem to prove one version of L'Hopital's rule. This is not the only version, there are several versions. Please check the notes. So theorem, L'Hopital's rule, 0 by 0 form. Just writing 0 by 0 makes my hand curl up in agony, but that is the way this is usually stated. If f and g are differentiable in the open interval AB. So I'm just going to take this to be a finite open interval. Suppose both f of x and g of x converge to 0 as x approaches b. Okay. If limit x going to b of f prime of x by g prime of x exists and is finite, then limit x going to be f of x by g of x is equal to limit x going to be f prime of x by g prime of x. Okay, so what we are essentially assuming for all this to go through is that g of x and g prime of x are never 0 on AB. Okay, that is being assumed here, otherwise the quotients won't even make sense. So the statement says that if you have two functions that are approaching 0 with the denominator never being 0, then the limit of the ratio f of x by g of x, which is going to approach 0 by 0 form, will actually exist if limit x going to be f prime of x by g prime of x exists. And not only will the limit exist, it will coincide with limit x going to be f prime of x by g prime of x. Okay, now here is one scenario where it is better to use the terminology and language that we introduced to speak about limits, such as some quantities being small as you get close enough to other quantities, so on, right? So we had introduced this notion of as you get arbitrarily close to and things become arbitrarily small and so on. By wording this proof in that language, the proof becomes really transparent and clear. Whereas when you write down the nitty-gritties in terms of epsilon and delta, the proof becomes really convoluted. So what I'm going to do is I'm going to just write the proof using the full force of language. Language, after all, is just a shortcut that eases the process of thinking. So I'm going to exploit the full range of our vocabulary in this proof. But nevertheless, this is an introductory course. Getting too comfortable with language might hide the difficulties and make you convince yourself that you have understood, when in reality you're just deluding yourself. So what I urge you to do is to read this proof, process it, understand it, and translate it to rigorous mathematics. Okay, not that the proof I'm about to give is not rigorous, it's just using a lot of shortcuts. Okay, now what is the idea behind the proof? Well, what we are going to do is just look at the interval AB. We are approaching the point B, right? Now what I'm going to do is, suppose the point X is here. I have to show that limit as X goes to B, f of X by G of X is equal to L. Just call this is call this L. Okay, limit x going to be f prime of x by g prime x, call it L. I want to show that this ratio also converges to L. What I do is, given this x which is close to b, I choose another t which is much closer to b. Okay, I choose this t will of course depend on x. I choose this t much closer to b. Now when you are very close to b, we know that f of t and g of t are going to be exceptionally small. In fact, by moving this t sufficiently close to b, we can make both f of t and g of t as close to 0 as we desire. Okay, and then what I'm going to do is I'm going to apply the ratio mean value theorem to the functions f and g between these points t and x. So given any x, I will always be able to find a t such that certain nice things happen, and that's essentially going to be the proof. Okay, so fix x in AB. Okay, we are going to prescribe how to choose t. Okay, now what does the ratio mean value theorem say? We are assuming that both g of x and g prime of x are never 0. So what we can do is this f of x by g of x, we can write it as f of x minus 0 by g of x minus 0. Correct? We can do this, and this is approximately equal to f of x minus f of t by g of x minus g of t, where this approximation can be made as nice an approximation as you desire by choosing t appropriately. Correct? Now because of this, we can write this as f prime of some c by g prime of c, where c lies in xt, Okay, now this as x approaches b, t also approaches b. We've just given an x, we can always choose t very close to b. Then c also approaches b, because c is squeezed between x and t. Okay, hence the above ratio converges to L. Therefore, the original f of x by g of x also converges to L. Now, this is a very rough sketch that illustrates the idea behind the proof. So let's make it somewhat better. This is a little bit too vague. Let's make it somewhat better, add some details. Okay, so we essentially get the idea how to choose this t. You choose this t very close to b, so that this approximation becomes very close to an identity. So what is it that we want to do? We want to analyze f of x by g of x minus L. Okay, we want to analyze this. Now what we are going to do is we are going to add and subtract terms involving f of t. Okay, f of x by g of x minus f of x minus f of t divided by g of x minus g of t plus f of x minus f of t by g of x minus g of t minus L. Okay, we want to make this quantity arbitrarily small if x is sufficiently close to b. Now, by triangle inequality, of course, we get f of x by g of x minus f of x minus f of t by g of x minus g of t plus f of x minus f of t by g of x minus g of t minus L. Okay, fine. And again, this is equal to f of x by g of x minus f of x minus f of t by g of x minus g of t plus mod f prime c by g prime c minus L, where c lies between xt. Okay, where c lies between xt. Now choose t so that this term, the first term is less than epsilon by 2. So fix epsilon greater than 0. Choose t so that the first term is less than epsilon by 2. Now we have choice of this t, and this choice of t depends on x. I have not told you how to choose x. Okay, only then can we proceed to choose the point t actually. So this should actually come first. So let me put the arrow this way. First choose x close to b such that mod f prime of y by g prime of y minus L is less than epsilon by 2 for all y in x comma b. So just choose this point x sufficiently close to b so that the ratio of the derivatives is already less than epsilon by 2 when you take the difference with the limit L. Okay, so first choose this x so that this happens. Now choose t sufficiently close to b so that this term also becomes less than epsilon by 2. Okay, combining both together we get mod f of x by g of x minus L is less than epsilon when x is sufficiently close to b. Okay, and this concludes the proof. Okay, so the only step that is actually vague is this choice of this point x is not really vague. I am just saying that there will be some point, for sufficiently close to b, there will be you can choose such that mod f prime y by g prime y minus L is less than epsilon by 2. That's just coming from the definition of limit. So there is no impreciseness here. The impreciseness is to say that this quantity can be made less than epsilon by 2 if t is sufficiently close to b. I leave it to you to determine in terms of the functions f and g how you have to choose this point t. That's not really hard, but it's clear that it can be done. You just have to expand this f of x by g of x minus f of x minus f of t by g of x minus g of t. You just have to expand it and analyze those terms and determine how you have to choose this point t. Okay, so I leave it to you to complete the proof. So this concludes this module. You're watching the course on real analysis, and you have just watched the module on the ratio mean value theorem and L'Hopital's rule.